All right, so let's get started. We are down to the wire, right? Two days left. So I want to talk a little bit about bookkeeping and about the schedule between now and the end of the semester, because we're starting to get down to the wire. Okay, so a couple things. I've decided to push back the due date of the design project 1 week to December 16th. Grades are due to Marshall by Monday at noon, and I can grade these projects pretty quickly, so I figured give you all as much time as possible. Okay, so the design project will be due to me instead of December 9th at 5 p.m., December 16th at 5 p.m. Plus, I know we've got a few folks in here who are contemplating taking the comprehensive exam, and it's also on December 9th. So, you know, that would be, you know, if I can make that an easier process, I will. So, does that sound reasonable? Okay. So tonight we're going to talk about fatigue, and then next week we're going to talk about constructability and deck casting, essentially. And that'll be it, because that's basically the long and short of fundamental bridge engineering. That's the long and short of it. A couple more things on scheduling. So on December 9th, next week, I will also be giving you a take-home final. But I want to very heavily emphasize it will be pretty short. Okay? It's not going to be an hours upon hours labored process. It's going to be mostly conceptual stuff. There will be a few calculation things here and there, but considering the amount of work you're putting in the project, a lot of these calculations are going to go real quick. Okay? It's not going to be a significant amount of time. I imagine if you're spending more than 2 hours total on the final, you're probably doing something wrong. You know, so, I mean, this will be pretty short. All right. Sound reasonable? Okay. I will give that to you on December 9th, and you just turn that in the same time that you turn in the project, December 16th. And I'll post everything on MU Online. I'll get everything up to date on Blackboard so that everybody can sort of follow through. Sound good? Okay, another item. I don't know if you all have been paying attention to your Marshall email, but course evals are up. Okay, now I noticed some of you have already done your course eval, and what I'm asking is for everybody to do the course eval. If you think I'm the worst professor you've ever had in the history of the world, you know, tell me, you know what I mean? In other words, do the eval, okay? I don't know about how other professors are, but I take them pretty seriously. So if you've got some significant comments that, you know, or some suggestions for improvement, I mean, tell me. You know, I want the class to be as good as possible. So yeah, so that's sort of my bit on that. So they closed next Friday. They don't take very long, so if you could do that, I would greatly appreciate it. All right. Any questions so far in terms of scheduling, bookkeeping, what comes next, the agenda between now and the end of the semester? Everybody good? All right. Now, just a heads up, we had one student who before break could not make their research presentation due to work requirements, so we're going to pause the recording for a little bit and take a few minutes and just knock this out of the way real quick, and then launch into our topic tonight, which is fatigue. Sound good? All right. All right, so we're back. All right, while I'm pulling up the lecture notes for tonight, a couple things. So I don't know if anybody noticed, but I posted a video in the playlist for this over break, and it's kind of long, and I know the Excel sheet's going to seem kind of daunting, but I kind of think of that video as the solution to homework 4. But not only is it the solution to homework 4, but it's probably going over 70 to 80% of what needs to go in your design project anyway. So the idea was it'll give you kind of an idea of how to set things up. I say it in the video, and I'll say it now. I'm going through how, you know, like how Greg set it up, how I set it up. You can set it up your own way because you're the ones building the sheet, so you do it your own way. But hopefully it provides a little bit of guidance, because I can imagine that when you start to put it all together, it starts to seem kind of daunting and whatnot. So hopefully it can kind of, streamline the process a little bit. My senior design folks are back there going, about that. All right, any questions? All right, so we have 2 topics left, and I want to talk about this. Now, I've mentioned this before. I haven't quite gotten the format updated yet. I was doing pretty good, and then these are my slides from a couple years ago, and everything's still valid. I didn't have time to get all my slides reformatted, so I went with it. So I've got the handouts and whatnot. We're going to talk a little bit about fatigue. Now, fatigue, a couple things I'll say about it. It is, from a mechanics perspective and from a computations perspective, it's actually kind of tough. It involves a lot of fracture mechanics and whatnot, and that can get kind of tricky. But all in all, the math that we have to do for fatigue is pretty simple. And once you go through this and sort of highlight it out, I think you're going to, this isn't really that bad. This is actually pretty straightforward. So, and I'll make a couple comments as it relates to your design project as well, because for some of you, fatigue is going to be a really big issue, and for some of you, it might not be a big issue at all. And it all depends, really, for you all, where your cross frames are. So, so let's get into it. So, fatigue is, it's this, it lurks in the background, and it's been lurking in the background through a lot of the stuff that we've been talking about this semester, and now it's time to actually start talking about it. Now, what's going on? Fatigue is a phenomenon that is related to systems that are subjected to cyclic loading. Particularly, that should be obvious by now that that's a significant issue with bridges. A bridge is loaded, unloaded, loaded, unloaded, loaded, unloaded, and that happens, thousands and thousands and usually millions of times throughout its design life. So we have to be able to assess that. Okay. What ends up happening from a mechanics perspective is that when you look at what I'll call fatigue-related details, things like stress concentrations, welds, bolts, any sort of disruption in the fundamental stresses in the bridge, anytime you see those areas of stress concentrations or regions with initial flaws such as welds, you can have some really serious issues. To give you kind of an idea, there are situations with certain details where steel has like a yield stress of 50 KSI, something about like that. Well, there are fatigue details that have a stress capacity of 12 KSI, much less. But it's just because of the way that the connections are oriented and the stresses that they're seeing, you can have much lower capacity under fatigue. Now, what is fatigue? I can read out the dictionary definition if you'd like. Fatigue is, when we talk about fatigue, we're talking about the initiation and propagation of cracks, okay? In other words, imagine, I've got this piece of metal or what have you, and there's a tiny crack in it. Well, imagine what happens if you're loading it and unloading it, loading it and unloading it. That crack suddenly is going to get a little bigger and a little bigger and a little bigger. And once a crack starts, it just tends to want to travel throughout the section, okay? Those cracks can grow and grow and grow and lead to some pretty big issues. And we've seen this happen before, even in some of our research presentations. I believe somebody presented on Yellow Mill Pond, if I remember correctly. Yeah, so that's what happened, right? There was a repeated loading cycle, a crack initiated, and went right through the girder, right? Well, this is exactly what we're talking about here. A lot of what the spec was written about, and a lot of where fatigue specs came from Yellow Mill Pond and situations like this. Now, fatigue failures can happen a number of ways, and I sort of mentioned this before, but ultimately it comes from one of two situations. Anywhere where there's an initial flaw or an initial defect, or anywhere that you have a stress concentration. Now flaws, I think that's pretty easy to understand. If you have a flaw in the system, it's going to sort of create a spot where a crack wants to develop. One of the things about a weld is in ways you're really creating a susceptibility at a particular point when you weld something. I mean, you're taking two pieces of steel and inputting a large amount of heat energy to essentially melt them together. So it's almost begging for an initial flaw, okay? That's just sort of, it is what it is, and there's really no way around it. Now, there are other situations where you can have a stress concentration. For instance, if you have a bolted connection. For those of you that have had, you know, basic steel design, I mean, I know we talked in steel design about shear lag factors. And I show a really, you know, pretty common picture where you look at the stresses in a piece of steel that's got a bunch of bolt holes in it. And you find that in the gross section of the member, the stresses are all nice and neat and uniform. But right there at the connection, the stresses are all over the place. That's why we use those shear lag factors from steel design. Remember, you take the net area and you multiply it by U, that shear lag factor. Because the stresses are going crazy right there around the bolts because you're creating stress concentrations. Stress concentrations, the stresses suddenly get higher. Well, high stresses lead to failures, so something to consider. Now, a lot of the stuff that we talk about with fatigue comes from a branch of engineering called fracture mechanics. If you're a mechanical engineer, fracture mechanics is a very common graduate level course. Most mechanical engineers take fracture mechanics in grad school. It's a very common class. And it's all about stress concentrations and points, like a particular point in a member where the stresses suddenly get larger and larger. And we call those points cracks, you know. It's where we have a stress concentration. There's a very critical parameter in fracture mechanics that I just want to introduce you to. And I'm not going to go crazy into this. I just want to give you kind of an idea. There's a very critical term called the stress intensity factor. It's kind of like if you took mechanics of materials, you know, very fundamental formula, sigma equals P over A, or My over I, very fundamental. Stress intensity factors are pretty popular in fracture mechanics. So to give you kind of an idea of what's going on, this is sort of a very typical fracture mechanics problem. The idea is we have some plate and we say it's, you know, infinitely long. We're trying to, you know, not worry about those dimensions. We're trying to keep it as simple as possible. And we're saying that the plate has an initial crack right here in the center. Okay? And, you know, I say that the crack is 2A long because I'm trying to use symmetry and say, well, 2A long, it's only A on the one end. Right there at the location of that crack, you know, right here and here, if you go through all the math and solve for your stresses, and that's where fracture mechanics and all that grad school math comes into play, if you go through and solve that out, you find that you've got some really massive stresses right here, okay? Now, the solution for that, and that's where, you know, grad school comes into play and whatnot, is, you know, this term over square root of 2 pi r. And this term here, we call that K1. And that K1 is what we call a stress intensity factor. The idea that applied stress over or times square root of pi times A being the crack width. Now this right here, this is sort of the most fundamental case in fracture mechanics. You know, an infinitely long plate with a crack in the middle. It's like the, you know, it's like if you did columns, like the simply supported column, the fundamental case. Then you say, all right, well, what if the column is fixed? What if the column has free ends or what have you? And then you start, you know, making the problem a little more funky. It's like you start here and then you go on. So this is the more fundamental stress intensity factor. But in general, we would adjust that by a couple parameters. We would adjust that by W relating to non-uniform stress fields. Instead of yanking on it, maybe we're bending it, maybe we're twisting it, what have you. We would also adjust that by a term Y relating to the geometry. Maybe it's not an infinitely long plate, maybe it's a finite plate, maybe it's a triangular plate, maybe it's a plate with a hole in it. All of that stuff. You can go back in the literature and probably find a lot of the stuff on Google. There's just pages and pages of here's your situation, here's your stress intensity factor, and what have you. Does that kind of make sense? This is just kind of some background stuff. Now, what ends up happening with fatigue is, you know, and with fracture mechanics is, you know, you're applying load the stresses around that crack are getting larger and larger and larger. And you start to reach a point where, oh shoot, maybe they're getting too large and that crack's beginning to propagate, and then it's starting to fail, right? I mean, think about it like this. Imagine if you had a piece of paper, right? Right? As soon as you make that initial tear, you've got a flaw in it. And you start applying load, it becomes an easier and easier tear, and suddenly the paper's torn in half, right? It's kind of the same idea, okay? There is a point when you reach a critical intensity, the member fails. We call that K1C, the critical stress intensity factor, and it's one of the most fundamental properties in all of fracture mechanics. What is that stress intensity factor that will cause the crack to grow in an unstable fashion, and the member fails? Okay. Now, that's fundamental fracture mechanics. Let's talk a little bit about fatigue theory. Okay, so fatigue theory is when we're talking about cyclic loading, the idea that the member is loaded and unloaded, loaded and unloaded. It's like, think about if you have let's say you open up a can of soda. You got a can of Mountain Dew, right? How many people rip the tab off? They don't like the tab. How many people do that? Anybody do that? You know, take the tab. How many people rip the tab off? Nobody rips it. Nobody's a tab ripper in here. Wow. Now, I imagine you have seen the tab off of the top of a can of soda ripped off before. How do you do it? Open it, and then you do what? Right? What happens over time when you do that? You take the can of soda and you do that a little. What happens? It gets softer, right? It gets softer and weaker, and suddenly it just kind of falls off, right? What's happening is under that cyclic loading of stress, you're exceeding that K1C, and it's just getting weaker and weaker. You start zooming in right there at that interface, you see those little cracks start to propagate. You get to a point where it's unstable, and it just pops off. Okay? That's kind of the idea. Now, excuse me. The idea is that we, in fatigue, we are applying cyclic loading. So from a stress standpoint, we're talking about not a stress value, but a range of stresses, a change in stress, right? Sigma max minus sigma min. Sound good? Stands to reason then that there would be a range of stress intensity factors, a change in Ks. Sound good? All right. Now, the idea behind fatigue theory is that we're trying to determine, how different parameters affect crack growth rate. That's what we're trying to figure out. Now, ultimately, that's going to be a matter or a function of a number of things. Number one, the number of cycles applied, N, right? I think about the can of soda, right? If I bend it once, yeah, it weakens it a little bit, but I've got to sit there and bend it over and over again before it fails, right? So obviously the number of cycles matter. That's point one. Point two, the flaw size. If it's a really, really tiny crack, maybe it's not as bad as if it's a really big crack, right? That obviously matters. And then the range of stress intensity values. Now go through fatigue theory, go through all the math, and you can develop a very fundamental relationship called the Paris equation. The derivative of the crack width with respect to the number of cycles is related to the following expressions. A times your stress intensity constant raised to a given power. Now, I'm not going to derive that. I'm not going to get into fracture mechanics for you. But you're going to see some very familiar terms when we start looking at fatigue capacity, and I did want you to kind of have a general idea of what's going on. Sound good? Now, ultimately, what you can do is you can say, all right, let's take this expression, and let's say, all right, let's go through, substitute our expression for stress and solve, and we can get that the change in stress is ultimately equal to A over N raised to a given power. All right, and what we'll end up finding is that for steel, some of those material constants are just that, are constants. For bridge steels, this value M, which is a material constant, is 3, and they found that from experimental tests on different connection configurations and what have you. So our change in stress is limited to A over N raised to the 1/3 power. And you're going to see that expression come up here in a second for finite life calculations. That value of A, it depends on what type of detail you're considering. Is it a cover plate? Is it a cross-frame connection? Is it a splice? What have you? That value changes depending upon your detail. Okay? The idea is that if you go through and do a bunch of fatigue tests on different configurations, for instance, if you're looking at welded beams, if you're looking at beams with in-welded cover plates, you find a general correlation among those given tests, among all the welded beams and among all the beams with in-welded cover plates and among all the cross frames and all of that. What we can end up doing is breaking those up into a specific set of categories we're going to see here in a second. Okay. Everybody okay so far? All right. Now, what we do in the bridge spec to make things a little easier to deal with is we develop what's called a fatigue threshold range. In other words, the idea is this. The more cycles that you apply, okay, the lower the stress is required to fail it, okay? Think about the Coke can, right? Bend it once, it's going to take a lot of bending to snap that tab off. But if I do it 10 or 12 times, it gets weaker and weaker. The more cycles, the less stress is required to fail it. And that's what's going on here on this plot. We've got the number of cycles, which it's plotted on a logarithmic scale, in case that parameter matters. But the number of cycles versus the stress range, the more cycles we apply, the less stress is required to fail it. Make sense? Well, what we do is we say, all right, when you get to a certain point, you find that, we just cap it off and say, okay, there's a given fatigue threshold that, we just sort of cap this off as our capacity. In other words, once you hit, I'll make up a number, 2 million cycles, we just cap the stress off at 12 KSI and say, well, that's going to be the fatigue capacity, for the rest of its design life. And that comes from experimental testing as well. So we call that a fatigue threshold. Okay, and the idea is that once you reach that, it doesn't matter how many cycles, that's going to be your maximum capacity. Now, there are some other factors that you might think might come into consideration, and ultimately we're going to see that they don't. For instance, what about material grade? In other words, does the fatigue performance of a particular detail change if I use 70 KSI steel versus 50 KSI steel? What happens there, right? Second, what about the minimum applied stress? That might be a little subtle, but I'll explain that here in a minute. But basically the long and short of that is, I'm talking about fatigue range. What about the initial load? If it initially had 5 kips on it versus 50 kips on it, does that matter? Well, we're going to see here in a second that they don't. So let's start off looking at material grade. Okay, so this is looking at, the same details, the same, connection details, looking at their fatigue capacity, but we've got A36 steel, A441 steel, A514 steel, all these different steel grades, but the same connection configuration. And what we're finding, not really much effect. Okay, that's from the test data. That's from all the experiments that have been done. Steel grade really doesn't affect fatigue capacity at all. In other words, 50 KSI steel versus 70 KSI steel versus 36, doesn't matter. In this world, steel is steel. It is what it is. Okay, so that's the effect of steel grade. There is no effect. Okay. Also, if we look at the effect of minimum applied stress, there's no effect on that as well. Now I think that this graph is a little confusing to explain what's going on when I say minimum applied stress. I think an easier graph to understand is this one. When we look at fatigue, what we care about is the range of stress that's applied. In other words, let's say that I start off with a girder that has no load on it whatsoever. Let's make up some numbers. So I go from a sigma max of 5 KSI to a sigma min of negative 5 KSI, because we know by now that girders can experience positive and negative bending, right? So if this is 5, and this is -5, what's the range? 10, right? Okay. I propose that this girder will behave the same as this one and as this one. In other words, this is from, let's say, what, 5 to -5. This one is from 0 to 10. This one might be from 15 to 25. But as long as that range is the same, as long as the fatigue range is the same, it's fine. That actually really matters if you think about it, because when we look at fatigue, we're going to be looking at the live load. It doesn't matter how much dead load was on the system beforehand. All we care about is the range of stresses that are applied due to the fatigue load. And that's it. Okay? Any questions? And this plot here is just showing different initial stresses, same behavior. Everybody good? All right. Okay. So let's take a moment and talk a little bit about what's going on in AASHTO, specifically the spec. I just realized I forgot to pass this around. I'm slipping on this stuff. Okay. So in AASHTO, we use 2 different ranges for fatigue capacity. We're either dealing with finite life capacity or infinite life capacity, okay? And it's a function of the number of cycles. In other words, if I'm talking about some bridge in the back of the woods that sees 2 cars a day, it's going to be governed by finite life, okay? But if I'm talking about an I-64 overpass that sees, you know, an ADT of 10,000 or something, that's going to be an infinite life fatigue category. It's all a function of the number of cycles, okay? Now we plot this relationship between the number of cycles and the stress range on what's called an SN curve, you know, stress range number of cycles. So if you ever hear engineers use the term SN curve, they're talking about fatigue. So this is generally what a fatigue capacity curve looks like, okay? Now they're plotted on logarithmic scales just because of the nature of the mathematics. The idea is this. For finite life, it goes back to the Coke can. The more cycles that you apply, the lower the capacity, right? For infinite life, we reach a given point where, you know what? It is what it is. It doesn't matter how many cycles that you apply. That's your capacity. So our capacity is either A over n raised to the 1/3, and that's that derived Paris equation that I showed you earlier, or we're capped off at a constant amplitude fatigue threshold. If your stresses are somewhere down here, you're good, because that stress is lower than what is required to fail it. If it's above that, we got problems. Pretty simple, right? Everybody good? Okay, don't worry. We're going to go through a pretty basic example. All right. So here's the long and short of it. The idea is that fatigue applied stresses have to be less than or equal to their nominal resistance. So let's talk about how we actually compute that in the spec. Okay. Now these are some examples of fatigue-related details. So for instance, did I give you all 6.6? Did I give you AASHTO 6.6? I can't remember if I did or not. I thought I did. I might not have, actually. If not, I can give that to you next week. It's no big deal. Section 6.6. It would have a bunch of images that look like this. I can't remember if I gave it to you or not. I'm getting the feeling I didn't, did I? Oh, well, no biggie. I can give this to you next week. That's no big deal. All right. So the idea is that based on a grand series of details in the spec, we can determine our fatigue categories. So for instance, like I said, fatigue details are those where you're introducing either potential flaws or stress concentration. So for instance, if I've got an I-beam, here's a fatigue-related detail, that weld right there between the bottom flange and the stiffener or the connection plate. Which that's one point I guess I should mention that I guess I really did kind of gloss over, and I probably shouldn't have. When we're talking about fatigue and we're talking about crack propagation, what we ultimately care about really are stresses in tension, okay? Because think about it, if I want to generate, a crack, where'd my little prop go? Here we go. If I want to generate a crack right here, really what I have to do is pull it apart, okay? If I push it together, it's really not going to, it's really not going to crack. Cracks and fatigue-related failures result from tension. So that's why we, in a situation like this, we're looking, for instance, at the bottom flange. We don't really care about the top flange. Top's being pushed together, and we really don't generate cracks in compression regions. That's really not the issue. Okay, so this is a potential fatigue-related detail. This is another fatigue detail. If you've got a splice, maybe we need to consider, that region right there where we might develop a crack. Maybe if we're looking at a cover plate, there are pages and pages of these details. And just saying it, you really kind of need to check all of them. But for most steel eye girder bridges, your two big ones that you're really going to need to check are details related to your splices and this, your stiffeners. Because other than that, those are really only the really only fatigue-related details that we see in most modern bridges. I mean, there's longitudinal stiffeners here and there are shear studs, but we're going to do shear studs later on tonight. So there we go. All right. Based on the severity of the detail, whether you're dealing with plain steel or a welded cover plate like what was going on the Yellow Mill Pond Bridge, we grade fatigue-related details. It's kind of like, was it like levels of service, right? And in transportation, or grades in classes and whatnot. We have grade A, which is like the best performance ever, hardly will ever fail, to E prime, which is the absolute worst case ever. All right, here's what it ends up looking like. Okay, so this upper graph right here, this is a category A detail. Okay, in other words, that is demonstrating the absolute best performance. This is a category E prime detail, worst performance. Okay, and as we go down the list, they get worse and worse and worse. Okay, so we have an A, a B prime, C, C prime, D, E, and E prime. Okay, everybody okay with that? As you go down, the behavior gets worse and worse and worse. Not really. It all goes from the test data that they did. And the long and short of it is that there are some general trends that you can find among some of the categories. Like, for instance, a lot of C's and C primes relate to longitudinal welds that are being loaded in direct tension, whether that's a stiffener or an end plate or something like that. But why they don't have a D prime or an A prime, I don't know that I have a great answer for you. It just, that's how Fisher decided to organize his fatigue details and whatnot. There really isn't a good answer. I'm sorry. That's what John Fisher at Lehigh decided to do. So, but it's also where the data laid in. Why they didn't just go A, B, C, D, E, F, G and just go like that? I don't know. Maybe they wanted to stop at F or something. I don't know. All right, that's the best answer I got for that. Okay, now let's talk a little bit about the loads. So we'll talk about the loads, the cycles that are applied, and then finally how to determine the resistance. Okay, so let's take that one at a time. First off, the load. Okay, now the fatigue load consists of just the truck. We're not looking at the lane, we're not looking at the tandem, we're not looking at just the truck, okay? But something to keep in mind, that rear axle spacing is not 14 to 30, it's fixed at 30, okay? And that just comes from the calibration that was done for the fatigue limits in the spec. They calibrated it off of the HS20, fixed with 30-foot fixed spacing. Actually, they calibrated it off the HS15, but we'll see how that comes about here in a second. All right, everybody okay with that? Okay. All right. Now, a couple notes regarding the fatigue load. So for impact, if you recall, we used 1.33 for all of our impact factors for strength and service. For fatigue, we're really only considering that single constant truck, so we're actually allowed to use a little bit lower of an impact factor. We use 1.15. Okay. Here, if you recall, now these we've actually already dealt with. Remember, how did we determine fatigue live load distribution factors? We took all the single lane loaded ones, right? And then we divided by 1.2. The reason why is because we're only looking at one truck, okay? So because we're only looking at one truck, we only use the one lane loaded distribution factors, and we divide by 1.2 because we're cutting out that multi-presence factor. Sound good? All right. Okay. So there's the load. Now we need to talk about the number of cycles. Now this is where the transportation stuff comes into play a little bit. The number of cycles that go on a given bridge is a function of the average daily traffic. Now I know my transportation folks in the room have at least heard that term before, right? Never. Not even you know, bringing up any term at all, right? All right, so average daily traffic, we need that data for a given bridge in order to be able to assess fatigue. Now, I guess I should take a step back and say, actually, no. You could just say, you know what, I don't care what the number of cycles are. I'm just going to go with infinite life because that's actually the most conservative estimate. And then who cares if 20 years down the line the traffic doubles? I know I can handle it, right? But, you know, we'll try and be a little scientific about it. So to start off, we need average daily traffic on a given road, okay? But that's not good enough, okay? We have to take that average daily traffic and convert it into average daily truck traffic. Now, if you've actually got the data, great, you know, great, that's wonderful. If not, we can use some approximations in the spec. So for instance, let's say you got 1,000 vehicles a day, an average daily traffic of 1,000 vehicles a day on a given bridge. And let's say that bridge is in the middle of Huntington. So it's an urban area, but it's not on the interstate. It's in the middle of Huntington. We can say, well, it's in the middle of a city. It's got 1,000 vehicles a day. Probably only 10% of that is heavy truck traffic. So instead of using 1,000 vehicles a day, we would use 100 trucks per day. Okay? So these adjustment factors are going to help us adjust average daily traffic to average daily truck traffic. Make sense? Okay. Now that's average daily truck traffic. Since we're talking about a single truck, we then must ask how much of that truck traffic occurs in a single lane. Okay. Now if you got a one-lane bridge, 100% of it, right? If you've got a two-lane bridge, we bump that down a little bit. And we say, well, only about 85% of that that truck traffic can really be assumed to act in a single lane. 3 or more, we say 80%, okay? Now, again, if you've got the data to back it up, I mean, use it. These are approximations, okay? Make sense? Now, you got the data, use it. Everybody good? So for my bridge in Huntington, if there's 1,000 vehicles a day, there's 100 trucks per day, but if it's 2 lanes, I'm only going to count 85 trucks a day, right? Sound good? All right. Okay. Now, this is one part of the spec I'm actually not a fan of. That used to not be like this. It used to be that the fatigue load factor was 0.75 and it was always 0.75. But now they've developed 2 load combos in the spec, and I'll be perfectly honest, I'm not a fan of it. They have fatigue 1 and fatigue 2. Fatigue 1 relates to infinite life, fatigue 2 relates to finite life. And the way that they've reported the fatigue amplitude, or the constant threshold stresses, and the way that they've reported the A's and N's and whatnot, they've actually got 2 different load factors. Personally, I think this overcomplicates the issue, but that's me, okay? So just wanted to sort of report that out. If it was, like, I wouldn't be harping about this if we were using the 2007 spec, because they didn't even go into this, and I thought it was much easier then. There is maybe some logic behind it. I still think it's a bad idea. they're trying to account for the possibility that over the year of the life, the truck will get heavier, you know, and that I think does maybe have some validity to it. Like, you know, back in the day, vehicular bridges just didn't see the loads that they do now. But they used to handle that in the spec differently, and I think they handled it before in a much clearer fashion. So I do apologize for that. Usually what they would do is they would just cut that in half and everything would be washed out. So ultimately the math achieves the same effect. I apologize for the complication. Now there is a nice little table here that's worth mentioning. What they've done in the spec is they've taken each of the fatigue categories and they said, all right, here's what the curve looks like. Here's what the curve looks like, right? So there's a point there where finite life meets infinite life, right? That point there at the bottom. So what they did is they took each one of those fatigue categories, each one of these fatigue categories that you see right here, and they said, all right, let's solve for the number of cycles that are required to reach that point. And if you've got more cycles per day, then you're in infinite life, less you're in finite. So it makes our life a little easier. So long and short of it is, for instance, if you're talking about a C prime detail, let's say, and you do all the math and you find that you've got 1,200 trucks a day on your bridge, well, then you're in infinite life, because anything more than that, that's 745, you're in infinite life. Does that make sense? Any questions on that? Okay. So if I want to determine the fatigue resistance, it's either constant fatigue threshold. If I'm in infinite life, finite life, it's A over N raised to the 1/3. And A over N, they're just lookups. And I'm sorry, I'll provide the tables next week, but I think you're going to see it's not really going to matter. It's pretty straightforward. Actually, never mind. They're here. I forgot I put them in the spec or in the presentation. So depending upon your actually, let's see. No, these are the fatigue thresholds. I'm sorry. Based on your fatigue category, here's your threshold stress. The one I want you all to pay attention to right now is this one right here, the C prime. Fatigue threshold stress for a C prime detail is 12 KSI. I want you to pay attention to that because we're going to do an example here in a second where that matters. Everybody okay with this? All right. Okay. Now, this is just some food for thought. If we are in finite life, we need the number of cycles. Now, how am I computing this? This term right here is the average daily truck traffic in a single lane, daily. How many days are in a year? 365. Why am I multiplying by 75? We assume in our design calculations that the design life of a bridge is 75 years. In other words, we assume that after 75 years we're going to have to replace that bridge. There's talk now of bumping that up to 100 years, but I think the jury's still out on that. I don't think they've made final decisions. There has been talk of upping some of these fatigue load factors to 1.75. It is what it is. We just sort of go along with what the code spec bodies say makes sense. This term N represents the number of cycles per passage. In most cases that we would deal with, it's 1. There are some instances where, like for instance, if you've got a really, really short bridge, let's say you've got like a 30-foot bridge. Well, you might have one truck running over that bridge, but it might generate 2 cycles of loading. I mean, think if you had a really, really short bridge. You have a truck run. Well, the front wheels run over the bridge, and that creates a cycle. And then the back wheels hit, and that creates another cycle. So if you've got a really short bridge, we actually say for every truck run, that's 2 cycles of loading. Does that make sense? Just because we're dealing with, we wouldn't do that on like an 80-foot bridge, but on a 40 or on a 30-foot bridge, that might be worth considering. Some other scenarios, we might bump those number of cycles up a little bit more as well. Does that make sense? Okay. Now let's look at an example. Now I've got this title as NSBA Example 2, a confession. This bridge that we've been looking at all semester comes from a document that is published by the National Steel Bridge Alliance, hence the NSBA. And they have a number of chapters in their Steel Bridge Design Handbook that are really worth looking at, and I'm going to provide some links next week, just sort of close out the semester. But they also have a whole bunch of design examples. We've been using Design Example 2 this whole semester. So NSBA Example 2, that's this bridge. Okay? So I want to look at the fatigue calculations for a given detail on this bridge. Now we're going to assume an average daily traffic of 5,000 vehicles a day. That's what we're going to assume. We're going to assume that the bridge carries rural interstate traffic. Okay? And we are going to investigate a cross-frame connection plate. Okay? Let's just see how this works. So to start off, let's determine whether we're in infinite life or finite life. Since this is rural interstate, I'm using a constant of 0.2, right? So 1,000 or 5,000 vehicles a day is 1,000 trucks per day. Sound good? Now, out of those 1,000 trucks per day, I'm assuming 80, since it's a two-lane bridge, 85% of them are going to go in a single lane. So y'all with me on that? So that's 850 trucks a day that I need to consider for fatigue. Everybody okay with that? Now, I'm going to go back a couple slides to this. We're looking at a C-prime detail. This is the number of cycles that meets that limit between infinite life and finite life. We've got, what, 850, something about like that? 745, we're in infinite life category, territory. Make sense? If we're in infinite life, that's our capacity, 12 KSI. So this tells us that we are in infinite life, and if we look at a C-prime detail, we have a fatigue threshold stress of 12 KSI. So that's our capacity, 12 KSI. Is the yellow not showing up on the handout? All right, I'm sorry. I will upload the PDF, all right? I just realized that. I remembered that 2 years ago that the yellow didn't show up. I'm sorry about that. I will upload the PDF. Does that work out? What's that? It'll show up just like this. I'm sorry. I should have remembered that. Whoops. I just noticed that there was a flurry of pens. It's like as soon as I started to put the like it was like on this slide, everybody was just like this, and then this, everybody starts writing, and I'm like, I remember. Sorry about that. Okay, so everybody okay with this? Okay, all right. So the capacity is 12 KSI. Okay. Now let's talk about the loads. Okay. Now, this is an image of the fatigue moments on the bridge, right? These are the fatigue moments. So remember, there's fatigue positive moments and fatigue negative moments, right? I am looking at a cross frame. Particularly, I'm looking right there, okay? I'm trying to pick the cross frame in the worst case location. The cross frames on this bridge are every 20 feet, right? So we're right here. Then 20 feet somewhere is about right there. Here's 40 feet. Here's 60 feet. That right there is probably going to be the worst case range of stresses, that cross frame. Make sense? So some of you all have a cross frame at midspan, right? Fatigue's probably going to be a bigger deal for those of you that have a cross frame at midspan than for those of you that don't. Like, for instance, I know there's a bridge that's 60 foot long and has cross frames at 20 feet. So who has that bridge? Anybody remember who has that bridge? 60 foot long, cross frames at 20 feet. Y'all are almost done with the project, right? Who's got the 60 foot long bridge with the cross frames at 30 feet? Anybody remember that? Ooh. It's going to be a busy couple weeks, isn't it? What's that? Yours is 80-20. So you've got a cross frame at midspan. So for you, you're going to check the moments right at midspan, and fatigue's probably going to be a bigger deal for you than some. Let's see. I think there's like a, what is it? I'm trying to remember some of the different parameters. I know there's a 60-20. You got the 60-20. So fatigue for you is probably not going to be that big of a deal because you don't have a cross frame at midspan. For you, you're probably going to have a cross frame somewhere like over here, and the moments, the range is just not going to be as bad. I'm not saying don't check it, but it's just not going to be as big of a deal for you. Does that make sense? All right. Everybody okay with this? Okay. Now, what I want is not the moments, but the range of moments. So if I do the math and interpolate, this comes out to be about 1057 foot kips. This one comes out to be about negative 286. So the range of stresses or the range of moments is somewhere like what, 1,300 something? Something about like that? Make sense? Okay. Now, this is live load. Live load goes on the short-term composite section, right? You all know how to compute that, right? All the moments of inertia and all that. So here's the neutral axis of the short-term composite section, okay? Now the centroid is 39.12 inches from the bottom to where the neutral axis is, right? What I care about is this distance right here, from the centroid to right there, because that's where the connection plate is, right? Because you're going to have some connection plate, filling in right here, and I'm looking at that well. So sigma equals my over I. I need the distance from here to that. Does that make sense? Everybody okay with that? Okay. So when I have that, here's my moments. There's my y. There's my moment of inertia, my over I. I get 7.18 KSI. That's less than 12, so I'm good. That's it. That's fatigue. Told you the math isn't that tough. It's pretty simple, right? You all already have all of the algorithms to be able to do all the linear interpolation. You can figure out the moments anywhere. You've got your section properties. It's my over I. That's it. So, does anybody have any questions about that? Everybody good? All right. Tell you what, let's do this. Let's take a little break, and then we've got one more big fatigue-related issue, studs, the stud spacing, because that is a function of fatigue. And then that'll be it for fatigue, because there's really nothing else to discuss with that. Everybody good? We say what, 7:50? All right, 7:50 we will reconvene.